here is about the pointing vector. So we have introduced the electromagnetic wave. So it is yeah. So it has the electric field component and the magnetic field component. They should be perpendicular to each other. Also, the E field and B field also perpendicular to the direction of the propagation, which is the direction of the pointing vector. And actually, the pointing vector has a magnitude equal to the energy transfer per unit area per time. Yeah. So it's actually like a area average power or something like that. And we also define the intensity like this. So here is here talk about the radiation pressure 光压，就是你幻想有个射灯照着你你会感受到一点光压，就是有一点射灯照着你，你会有一点点感觉，你真的不看着它。When a surface intercept electromagnetic radiation, a force and pressure are exerted on the surface. If the radiation is totally absorbed by the surface, the force is like this. Actually, I is the intensity of the radiation. A is the area, and C is the speed of light. So actually, is proportional to the area and also to the intensity of the radiation. And if the radiation is totally reflect back along its original path, so the force is 2 times to this one. So it's somehow like the collision 什么弹性碰撞那种。So if it is totally absorbed, so somehow like there's a surface and this is the radiation. If it is totally absorbed, so there's nothing going back. So this force is half of it. So it is IA over C. If it is reflected means something going back. And of course, this is a EM wave. So the speed entering and going back should be the same. So it should be speed of the light. So in that case, this force should be F equals I AC. So the intensity of this radiation shouldn't change because it is totally reflect. And in that case, this force should be 2 times to this one. So then suppose this one add with this one. The total force should be this one. And that's why there is an additional factor 2 here. I've tried to consider why the expression will look like this. So so I consider like this. F should be somehow like dP dt, and for delta P delta T, approximately as delta P delta T. So we have something like 2 delta U over C over C over C. And this should be 2IA over C delta T here, delta T here, and this should be 2IA over C. So actually, for total absorption, the radiation pressure is normalized by the area. It's normalized by the area. So this is the pressure. This is the force. So which is like PR is F over A. So it's only I over C. And if it is totally reflect back along the path, so PR is this term divided by A, so it is 2I over C, 2I over C. So actually, this type of characteristic is the particle characteristic， 就是粒子的性质才会有这种特性。如果是一个破洞的话，不应该有什么力啊，或什么动量啊之类的特性。那在第38章的时候，我们会讲多一些所谓的波粒二象性然后光有波粒二象性，然后粒子也有波粒二象性就是波有粒子的性质，粒子也有破洞的性质就是很玄的。So this slides talk about the polarization. Actually, yesterday I showed you a video about the polarization and somehow relate to this one. So I will talk about it here. So electromagnetic waves are polarized if their electric field vector are all in single plane, called the plane of oscillation. Light waves from common source are not polarized. That is, they are unpolarized or polarized randomly. 所以一般那个光源它是没有极化的，没有 polarized 的。那它就是每个方向它都会有一些电场在振动当然它每个方向的振动它都会随着它垂直的方向会有一个相对应的一个磁场在振动所以就是每个方向都有。那这个散乱的振动它就叫做 unpolarized。那如果它只有这个方向的我们就叫做 polarized, vertical polarized. This is called vertical polarized, or maybe in this direction, this is called horizontal polarized. So in the previous slide, we talk about we assume that the point we consider is far away from the light source. So we have the plane wave assumption, so which makes everything easier to explain. Maybe the math is also easier. So you can see we have the E field in the x-axis, and the B field in the z-axis. and the z-axis. Actually, x is in y-axis. E is in y-axis, and the B is in the z-axis. So this wave is propagate in x-axis. Okay, so if we try to symbolize the unpolarized light, so maybe we can just decompose it, all the E component in x, in z direction and y direction, and add them together. So actually they can sum up to be horizontal polarized component and a vertical polarized component. So if the light consists of both horizontal and vertical polarized component, we said that it is unpolarized light. So actually, if we have something like a polarizing sheet or a filter polarizing filter, we can make the unpolarized light to be polarized. Maybe this polarized sheet is direct vertically, so that only the vertical polarized light can pass through this filter. So that suppose the incident light ray is coming from here to here. So only the vertically polarized light can go through this filter. So the sheet is polarizing axis is vertical, so only vertically polarized light emerges. So if the original light is initially unpolarized, the transmitted intensity I is half the original intensity, I0. So suppose the intensity of the incident light is I0, and this is I, so this is I. So pass through a polarizing filter or polarizing sheet, so the intensity become half of the original, so 1/2 I0, something like this. So this is easy. So you can assume half of it is radical polarized, half of it is horizontally polarized. So half of it cannot pass. So it only half of the intensity remains. And the next case is if the original light is initially polarized, the transmitted intensity depends on the angle between the polarizing direction of the original light and the polarizing direction of the sheet. So it becomes like this. This is not the same as what we expect from the classical mechanics. Suppose you consider it a classical physics or classical dynamic point of view, you will expect we have polarizing E field in this direction, and this polarizing filter is vertically. So the y-axis component is actually EY cosine theta, and this is EX sine theta. So maybe you will expect I0 cosine theta rather than I0 cosine theta squared. But actually, this one can betterly predict the phenomenon which we have watched yesterday in the video. So actually, we need to multiply it by cosine theta squared rather than cosine theta. So for this case, the original line is initially polarized. different from the this case. This case is in this incident light ray is unpolarized, pass through this polarizing filter, so the output has an intensity half of the original. But for this one, the original light is initially polarized, and the direction of the polarization and the angle between the polarization angle and the angle between the polarization of the light and the polarization of the filter is theta. So the output multiplied by cosine square theta, something like this. So here is an example. So here we have incident light to have an intensity I0. So the figure shows a system of 3 polarizing sheets in the path of initially unpolarized. So this incident wave is unpolarized light. So the polarizing direction of the first filter is parallel to the y-axis, so in y-axis, and that of the second is at an angle 60 degree counterclockwise. So this angle is 60 degree counterclockwise on the y-axis, and then the third sheet is parallel to the x-axis. So this is parallel to the x-axis. What fraction of the initial intensity I0 of the light emerges from the 3-sheet system, and in which direction is that emerging light polarized? So suppose just like what we watched yesterday, if we don't have the middle filter, so it should be totally black. All the light should be blocked by these two sheet system. But suppose we insert something inside, something strange happen. The output should have some light, at least better than nothing. So here we need to calculate what is like. So actually, it's nothing but using this and this equation. So before sheet 1 unpolarizing, this is I0. So first of all, this is unpolarized. So it has an intensity I0. So after sheet 1, so it become vertically polarized, and the intensity should be 1/2 I0. So this is I1, and this filter is vertically polarized, so it becomes vertically polarized, right? So next, after the second one, so these two have an angle of 60 degrees between them, which means that next should have a polarized angle like this, and the I2 should be I1 cosine square 60 degree, something like this. Should be 1/2 I0 cosine 60 degree is 1/2 square. So it should be something like 1/8 I0. So this is I2. So for I3, this one and this one have an angle of 30 degrees. So it turns out that it should be horizontally polarized, and I3 should be I2 cosine square 30 degree, and which is nothing but 1/8 I0, and then square root of 3/2 square. So it's 3/4, 3/4, which means 3/32 I0. Or we can write it as 0.094 I0. So which is in x-axis, So this is any questions? So next is about reflection and refraction. Reflection 是反射，refraction 是折射折射。那我觉得你们中学的时候应该学过那个 Snell's law 那个这个。那 reflection 的话比较简单，就是入射角等于反射角photograph showing an incident beam of light reflected and refracted by a horizontal water surface. So this is the incident. This is the reflected. This is the refracted. So a ray representing of A. The angle of incident is theta. So this is theta 1, this is theta 1 prime, and the refraction angle theta 2. So when a light ray encounters a boundary between two transparent media, a refracted wave and a refracted wave generally appear as shown in a figure above. So the law of refraction, a refracted wave lies in the plane of incident and has the angle of refraction equal to the angle of the incident, both relative to the normal. So actually for reflection, law of refraction, this is very simple. It's nothing but theta 1 equals to theta 1 prime, 入射角等于反射角。So it's mentioned about the normal line, which means the line perpendicular to the surface So 这是那个正教的线或者是面吧，然后这个夹角是跟那个 normal plane 的夹角。就是 theta 1 equals theta 1 prime. So for the next case, it is about the refracted wave. So the law of refraction, which is called the Snell's law. A refracted ray lies in the plane of incident and has an angle of refraction theta 2 that is related to the angle of the incidence theta 1 by this one. So n1 and n2 is a dimensionless constant and called the index of refraction. Index of refraction. This is associated with a medium involved in the refraction. 它是跟那个物质有关的，就是什么空气是1然后水就是比较高，玻璃又比较高之类的。And actually, this index of refraction is inverse proportional to the speed of light in that material， 就是跟那个光速在那个物质传播的在那个物质的光速成反比的这个 n。 就是光在那边走得越慢，那这个 n 就会越大这样子啊。Or sometimes we may write it as, actually when I learned it, I something landed like this: sine theta 1 over sine theta 2 equals n2 over n1, n2 over n1. N2 over n1, or actually it should be something like a c1 over c2. So actually in the air, the speed of light is c, which is 3 times 10 to 8, and in the water, the speed of light is becomes slower. So this is smaller. So you can see that this angle is larger in the air and smaller in the water. Something like that. 我以前学那个电磁学要上2个学期，就是物理之后要上那个电磁1、电磁2。那电磁2的时候啊，要学这个的时候，这不是那么简单的。我那时候要学的时候是E view B view 的什么偏振，然后要算这个反射的那个 component 啊变成多少，折射的 component 变成多少，然后写一大堆大串式子，那个可以用那个 Maxwell equation 去算出来的，很可怕的。So this is about the chromatic dispersion of white light. 这个叫做色散。这个 chromatic 就是光嘛，dispersion 就是散开。The blue component is bent more than the red component. So passing from the air to glass, the blue component end up with the small angle of refraction. So passing from the glass to the air, the blue component ends up with the greater angle of refraction. So each dot line represents the direction in which the light would continue to travel if it were not blended by the refraction. So which means that so suppose the incident is a white light, so it consists of different types of lights with different frequency or wavelength. So actually, if you still remember, the red light have a longer wavelength, the blue light have a shorter wavelength, and in that case, so suppose we consider this angle. For red light is smaller than the blue light. So it's called the blue component ends up with a smaller angle refraction. The small angle refraction, and the red line have a larger angle of refraction. But in terms of change of direction, so the red line becomes smaller. And similarly, so this is air going into the glass. And here, if we have a going from the glass into the air, it is similar like this. So we can see that, suppose we consider this angle for the red line is smaller than the angle to the blue light. So it mentioned that blue is always bent more than the red. And actually, in the spectrum of the visible light is not only red and blue. There is a continuous spectrum. So, but it's only specify red is has a longer wavelength, and blue has the shorter wavelength. And this makes different colors will have a different angle of bending. So for the incident wave, we can see it is a bright light, but the output wave will become like something like a rainbow. Yes. Yeah. So here we talk about total internal refraction, 全反射. Rate of monochromatic light from a point source. And so this is the point source. This is the point source incident on the interface between the glass and air. Glass and air. So this is glass, this is air. And as the angle incident increases, the angle of reflection increases for the ray. For the ray E, it is 90 degree. So for this one, or something large enough, then you can see that this angle is 90 degree. So you can check back here something like suppose let me see. Suppose you're going from dense, which means that this one is large. This one is large. Yeah, this one is. Yeah, this one is larger. This one. We see. And yeah, N1 should be larger. N1 is larger. N1 is larger than N2. And in that case, theta 2 should be larger than theta 1. N1 is larger than N2. N1 is larger than N2. So this factor should be smaller than 1. And suppose we can just try to pick psi theta. Psi theta 2 equal to psi theta 1 N1 over N2. And actually, N1 is larger than N2. So this term is larger than 1. So if this one equals to N2 over N1, is equal to N2 over N1, then this one will become 1. This term will become 1. And this is 90 degree. But if it is furtherly larger, become larger than this one, then this whole term will be larger than 1, and there shouldn't be any solution to that one. That is no real solution to that one. Maybe you can find it in the complex domain. So in that case, suppose theta c is large enough, then you'll see that the refracted angle is 90 degree. So if you further increase the angle of the incident angle, then all the waves should be reflected. And this is called the total internal refraction. And actually, there is another phenomenon called the frustrated total internal refraction frustrated 就是很沮丧的意思嘛，就是很沮丧的全反射。那为什么很沮丧？就是说，so this one is called the total infernal refraction. Suppose we have maybe this is glass, and suppose this two is far enough, and this angle is larger than that, called the critical angle. Then yeah, you can expect all the incident light to be refracted. And suppose these two are touching each other, which means that it feels like there are no air in between these two glasses of three frames. So all the light will go through. There will not be total internal reflection. But suppose we place these two frames close but not touching each other, then some of it will be reflected and some of it will go through. This is very interesting. So when two such streams are sandwiched back to back and pressed together, the air glass interface can be made to vanish the beam, then propagate onward undistributed. So this is this case. And this transition from total to no reflection occurs gradually. 它不是一下子从那个 TIR 变成no reflection. It's not certainly from TIR to no reflection. It occurs gradually, 渐渐发生的 as the air stream is made to thin out by progressively squeezing the stream together harder until they make intimate contact. So the optimally speaking, if the evanescent wave extend with the appreciable amplitude across the rare medium into a nearby medium of higher reflective index, energy may flow across the gap. This is called a frustrated total internal reflection. 那这个现象啊，我们在第38章学那个量子力学的时候会学到一个，就是叫做串穗效应的跟这个是蛮类似的，它就会有一些是看起来它应该传反射，但是它中间有一个缝隙，它就会有一些部分能够穿越过去，然后有一些就是被反弹回来这样。So this is the refraction indexes. So for vacuum or air is like 1 or 1.00029. For water is 4 for 3. And some other material, sugar solution. And for diamond, it's 2.42. So that's why ladies like the diamond much. And yeah, so in this table, at least a diamond is the highest refraction indexes